Good morning, students. So today let us discuss plane wave solution of Dirac equation. And we have been studying relativistic equations in relativistic quantum mechanics, mainly two equations. One was about Klein-Gordon equation, then another one was about Dirac's equation. So two equations, they represent relativistic quantum mechanics, relativistic equation in relativistic quantum mechanics. They are very important equation as far as this relativistic quantum mechanics is concerned. And Klein-Gordon equation mainly says about the second order differential equation in space and time symmetry. So second order differential equation in space as well as second order differential equation in time. And of course, it did not say anything about the spin. The spin of the particle was considered as 0. We know that the spin component is represented as 2s plus 1. And so in case if we are going to substitute s equal to 0, then we will have only answer as 1. I repeat, the psi in Klein-Gordon equation says about only one component, whereas the spin component is represented as 2s plus 1. The total components of the spin will be 2s plus 1. As I said just now, the Klein-Gordon equation says for the spinless particle s equal to 0 for k meson and for pi meson. Suppose if I am going to substitute s equal to 0 in calculating the total component of spin 2s plus 1, I will get to answer as 1. So this Klein-Gordon equation represents the scalar particle, the relativistic equation for the scalar particle. This is a main discrepancy. Dirac equation solved this problem. Dirac equation automatically it involves the spin, the consequence of spin, through Pauli's matrices. In Dirac Hamiltonian, we know that alpha is connected with the Pauli's matrices. Alpha is a 4x4 matrix. Beta is an operator. Alpha is also an operator. Okay, alpha is connected with Pauli's matrices. Pauli's matrices are spin operators. And what is this beta? Beta also is an operator. It's a scalar operator. Alpha is a vector operator. So this 4x4 matrix, we will get the solution as 4 solutions. We will get the solution H psi equal to E psi. So for energy we will have 4 solutions. What are the psi? Psi has 4 components, a column vector. In Klein-Gordon equation, psi was only one component, whereas in Dirac's equation, psi has 4 components: psi 1, psi 2, psi 3 and psi 4. So this is a column vector. Since it's a column vector, and surely we will have the energy values, surely we will have as 4 solutions. So spin automatically is the consequence of this equation. That's the beauty of Hamiltonian, Dirac's Hamiltonian. Also, another very important thing is, of course, it is symmetry in space and time. This is first order differential equation. Look at this equation, P equals minus I h cross partial d by dx, and H psi equal to E psi, E equal to I h cross d by dt. So this is single order, only one order differential equation. It's a very simplest one. It's a linear equation. It's a homogeneous equation. So linear and homogeneous equation. It's a very elegant equation. It represents for fermions, which we want. So Klein-Gordon equation represented only for spinless particle where s equal to 0, whereas it represents for all the fermions. Okay, it's a linear equation and homogeneous equation. So with this introduction, we are going to discuss the plane wave solution. We discussed already the plane wave solution for Klein-Gordon equation, and we arrived energy values as 2 values. One is positive value, another one is negative value. Here also we are going to get both positive value and negative values. But thing is, in addition to that, the positive value has two solutions and negative value also will have two solutions. 2 plus 4, 4 will have 4 solutions. So that's the idea. Because it contains 4 components. So your alpha contains 4 components, beta also contains 4 components, psi also contains 4 column vector, 4 components. Ultimately the energy also will have 4 solutions. So that's the idea. So our idea is to find out energy and psi. Okay, energy and wave function. So we'll go into the discussion. So plane wave solution of Dirac's equation. So as I said, this is 4 by 4 matrix, alpha and beta, a column vector with 4 rows of psi. So psi is a column vector. Dirac's equation is equivalent to 4 simultaneous first order differential equations that are linear and homogeneous in 4 components. So for any homogeneous equation, we know that the solution will get as determinant equal to the coefficient of determinant must be equal to 0. We want to get for any matrix the solution, the coefficient of determinant should be equal to 0. Only then we can say that it's a homogeneous equation. So we have already learnt in mathematical physics. Okay, so these 4 components are there. Now we are going to have this plane wave solution as we assumed the same solution in plane garden equation. Okay, here too we are going to assume the solution. So we now try plane wave solution is of the form is exactly as it is given in equation 8.63. Here j equals 1, 2, 3, 4. So 4 components. So 4 vectors. Okay. So these psi j's are eigenfunctions of energy and momentum with eigenvalues p equal to h bar k and E equal to h bar omega respectively. We know already this. So Dirac's equation is given by just now the Hamiltonian. As I said, this is we are going to take the Hamiltonian. H psi equal to E psi. So E psi instead of psi we are going to replace with U. U is a 4 column vector potential into 2 component column vectors. As I said, E has 4 solutions. Okay. Ultimately we will achieve two solutions. One is a positive value, then another one is negative. Positive value will have 2 solutions and negative energy also will have 2 solutions. So add together that will have 4 solutions for E. Okay, U is the column vector. And as I said, these are all 4 by 4 matrices. Okay, 4 by 4 matrices. U is a column vector. Now, as I said, U has a 4 components: U1, U2, U3, U4 in a column vector. And we are going to arrange in such a way that V has U1, U2. The first U1, U2 is represented in terms of V. The last 2 components represented by W. So W equals U3, U4 to simplify. Okay. So now we have converted into 2 by 2 matrix. At the end we are going to have 4 by 4. So now you substitute this into this equation. So E, I have written E. Instead of U, you can substitute VW in a column vector. So VW, which is equal to C, okay, C alpha dot P. 2 by 2 matrix, alpha dot P can be written as, of course, as I said, alpha is connected with the Pauli's matrices using this relation. Your alpha x equal to 0, sigma x 0. Similarly, sigma y, for sigma y as well sigma z. Okay, 3 Pauli's matrices exist. And beta equals I0, 0 minus I. So we know identity matrix. Now you substitute. So now alpha dot P can be written as 0, sigma dot P 0. Okay, in terms of 2 by 2. So this will be your 4 by 4 matrix. In terms of 2 by 2, we can write this multiplied by P will give you this. And your U multiplied by U in a column vector as VW in a column vector. Plus you just pull MC squared out. It's a value MC squared. And P beta matrix can be written as I0, 0 minus I VW. Is it okay? This equation is very simple equation. Now you just multiply this. You are going to have matrix multiplication. So 0 multiplied by V, sigma dot P multiplied by W, sigma dot P multiplied by V, 0 multiplied by W. And we have this. Very simple one. See, 0 multiplied by V, sigma dot multiplied by W, sigma dot multiplied by W, sigma dot P multiplied by W. The next one will be sigma dot P multiplied by V plus MC squared VW. Is it okay? Very simple matrix multiplication. And I can write this equation as exactly plus MC squared V minus mc square w. Okay, so this equation can be represented in terms of this equation. Now just to compare the components. So your EV equals this part, EW equals this part. Is it okay? Your EV equals this part and EW equals this part. You pull this mc squared v this side, similarly minus mc squared w to left hand side. So we have this equation E minus mc squared v, correct? I have pulled v out, common out, which is equal to C sigma dot T W. C E plus mc squared w equals C times sigma dot T v. So these two equations are very important equations. We are going to get all the solutions from these two equations. One represents minus, another one represents plus. Okay, so our aim is to find out E. First one is E, then V and W. Our aim is to find out energy eigenvalues and the corresponding wave functions V and W. So V and W means U1, U2, U3, U4, which is nothing but your U. Okay, U is your complete wave function in a column vector. So our aim is to find out energy eigenvalues and corresponding wave functions out of these two equations 8.70 and 8.71, which are very important and base for Dirac's solution. So remember that each one of these represents two equations as sigma is 2 by 2. As I said, sigma 2 by 2 matrix. And V and W are two component column vectors. Okay, V and W are two component, sigma also 2. Multiplying equation 8.70. So this is your 8.70. You are going to multiply with E plus mc squared. So take this equation, you are going to multiply with E plus mc squared. So E plus mc squared multiplied by E minus mc squared V equals both the sides. So E plus mc squared C times multiplied by sigma dot P W. So we know this equation just now 8.71. As I said, you just remember those two equations aside. So E plus mc squared W equals C times sigma dot P V. Okay, you just substitute E plus mc squared. E plus mc squared W. E plus mc squared W can be written as C times sigma dot P V. You substitute here. So we'll have C multiplied by sigma dot P, one more C, correct? One more C multiplied by sigma dot P V. So you have C squared sigma dot P whole squared V. Is it okay? And left hand side you have A plus B whole squared formula, you know. So A squared plus B squared. No, A squared minus B squared. A plus B, A minus B, that will give you A squared minus B squared formula. So E squared minus M squared C power 4 V, which is equal to C squared times sigma dot P whole squared V. This sigma dot P can be written as a parallel because this is a dot product. It can be either parallel or anti-parallel, 0 degrees or 180 degrees. If it is parallel, then this must be plus P. If it is anti-parallel, this must be minus P. In both the cases, we are going to square, this becomes P squared. So sigma dot P whole squared equals P squared. So this can be replaced with P squared. Okay, in the earlier equation, so we can replace this as P squared. So E squared minus M squared C power 4 multiplied by V, which is equal to C squared P squared V, which is equal to 0. I can take the common term out and I can write the remaining terms, which is equal to 0. So either this can be equal to 0 or this can be equal to 0. This cannot be equal to 0 because, see, look at this, is a non-trivial solution. So V cannot be equal to 0. If V equal to 0, what will happen? There will be no wave function, no particle exists. Okay, which is not the case, which will not be the case. So V cannot be equal to 0. Only possibility is this can be equal to 0. If this is equal to 0, and this will have two solutions. See, E has two solutions now, positive energy and negative energy, as we have seen already earlier in Klein-Gordon equation. Klein-Gordon equation also we approached the same two solutions, positive energy and negative energy. Only thing is, it couldn't explain the negative energy solution, that's all. Mathematics and all very correct, very simple, very elegant. Okay, so your energy E equals now plus or minus C squared P squared plus M squared C power 4 to the power 1 by 2. So Dirac equation gives positive and negative energy solution. So we are going to get only the solution. So we have got the solution for E now. And of course, as I said, positive energy will have two solutions, negative energy will have two solutions with the inclusion of spin. So that's the idea. We know that spin will have two components, spin up and spin down. So your two solutions will be one for spin up, another one is for spin down. The negative energy also will have spin up and spin down. So totally 4 solutions. That's all. Is it okay? So we have positive and negative solution, two energy solutions. For each one we will have spin up and spin down. So totally we have 4 solutions. So that's the idea. Okay. So we shall now determine the energy eigenfunction. So we are going to determine now V and W. We have already discussed E. Okay, we have got the solution now. Okay, positive and negative energy solutions. Now we are going to get V and W eigenfunctions. So there will be 4 independent solutions, 2 for E plus and 2 for E minus. So in principle, one can use either equation 8.70 or 8.71. Both the equations can be used. So these are the equations. This is 8.70. This must be your 8.71. Now I can keep this for E plus or this for E minus, or otherwise I can keep this for E minus or this for E plus. I can take, but it says that from that equation the wave function V equals C sigma dot P W divided by E minus mc squared. Suppose if P equals 0, P equal to 0 means only for non-relativistic case, P approaches 0. If P equal to 0, it implies that E minus mc squared V equal to 0. I repeat, we can choose either this as E plus, this as E minus, or this as E minus, or this as E plus. But we are going to choose only this equation as E minus. What is the reason? The reason that we are going to see. Out of this equation, for the non-relativistic case, when P approaches 0, that is P equal to 0, then this equation becomes exactly like this. Now, when P equal to 0, I am going to consider this as E plus, which is equal to mc squared. V becomes indeterminate. That's the reason that we are going to keep this as E minus and this for E plus. That's the reason. We are not going to keep this for E plus and this for E minus. The reason is behind this slide. Okay, this is the reason. So we are going to keep 8.70 as for E minus solution, and this is for E plus solution. So hence equation 8.71 is used with E plus, 8.70 with E minus. For convenience, we may take V and W to be arbitrary, and then we are going to determine the one another. So we are going to determine V and W eigenfunctions. Now E plus eigenvalue.